Physics 2212, Lab 3, Magnetic Field of a Bar Magnet by Jacob Cook. Introduction. So description. So the goal of this lab is to observe and better understand magnetic fields through a visual representation, to visually observe the relationship between distance and magnetic field, and to use the distance dependence of magnetic fields and the Biot-Savart law to find the magnetic moment of a bar magnet. So here are some fundamentals. We'll be using a bar magnet to model a magnetic dipole. We are using the Biot-Savart law as displayed by the equations on the screen. And another key concept is distance dependence formula of a bar magnet. So the results we got from this experiment is mu equals 2.21 a amperes times meters to the squared, and then n equals negative 2.5, which is the slope. So assumptions, we assume the bar magnet acted as a magnetic dipole in order to apply the Biot-Savart law. These two pictures show a magnetic dipole. You can see that it points out from the north side of the map, the positive charged side of the magnet, and into the negatively charged side of the magnet. So the system and surroundings. So the system is the bar magnet, and the surroundings is everything else. The initial conditions are the bar magnet and magnetometer on the phone, which measures the magnetic field at certain positions. So the details of the experiment is first, the location of the magnetometer on the phone was pinpointed by sliding the phone perpendicular to the ruler, both vertically and horizontally, with the bar magnet on one end of the ruler in order to see at which point the phone relative to the magnet, the strongest magnetic field was read. So here's the system. You can see the meter stick, the magnet on the left side, and the magnetometer, which is the phone, and you slide it up and down as shown by the right. So here are some of the calculations that we got, and you can see there is a correlation in that right graph that the farther you get from the magnet, the less the magnetic field is. Here are some more calculations we did. And so the observations, as I mentioned before, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The position of the phone matters in terms of ensuring the magnetic field of the Earth doesn't interfere with our reading for the magnetic field of the bar magnet. We made these two magnetic fields orthogonal to each other, so they're on different axes, so they don't affect each other. So here are some of the calculations we did. We used the distance dependence equation, which is 3.043 x minus 14.633, n, which equals slope, which is negative 3.043. We used the Biot-Savart law to find mu. So we knew the r radius, which is the meter stick, is 1. We set the Biot-Savart law equal to the distance dependence and solved for mu. Mu is 2 pi kr to the n r to the third over mu. And then we find that m equals 2.21 a 2 times m squared. So here's for the GlowScript Python coding section. So we established physical contents, and we created the magnet at the origin. And then here we create a function for the magnetic field created from that magnet. And in the bottom section, we are creating certain positions that will eventually read the magnetic field at these positions. Here's the coding. So we're drawing the magnitude and direction in the form of arrows at these positions, as I mentioned in the previous slide, on the left side. And on the right side, we are drawing these the magnetic field at locations 45 degrees from the magnet. Here's the picture that we got. As you can see, this is accurate to what we would expect, except for the 45-degree angle magnetic field. It should be pointing in the negative x and negative y direction. You can see here are the magnetic fields at certain places. So final thoughts. What if you hadn't oriented your experiment to compensate for the magnetic north? If we hadn't done this, the axes, they would be on the same axes, so it would be hard to determine what the magnetic field due to the magnetic north on the Earth, and then what is the magnetic field from the bar magnet closer to the magnetometer. What if you were to stick two identical magnets together end to end and run again? How would you expect the measurements to differ? I would expect the magnetic field to increase. Thank you.